For decades, astronomers assumed the universe looks roughly the same everywhere. Dense regions, emptier regions, but on the largest scales, it all averages out. That assumption underpins nearly everything we measure, from cosmic expansion to how galaxies and black holes evolve. We believe we're seeing a fair sample of reality. But what if we're not? What if the Milky Way sits inside a vast cosmic emptiness, so large it quietly distorts our measurements of the universe itself, not because our instruments are flawed, but because our location is? Observations from the James Webb Space Telescope and decades of galaxy surveys suggest exactly that. Our galaxy appears to lie within an enormous underdense region nearly 2 billion light-years across, known as the KBC Void, a structure that may be reshaping how we interpret cosmic expansion and large-scale evolution. Tonight, we'll explore the unsettling idea that our cosmic address is misleading us, and that some of cosmology's biggest contradictions may be artifacts of where we stand. If you enjoy exploring the universe's deeper and stranger possibilities, consider liking or subscribing. It truly helps the channel continue these journeys. Now let's begin with the discovery that forced astronomers to ask a dangerous question. What if the universe around us is unusually empty? On the largest scales, the universe is structured like a web. Galaxies cluster together along immense filaments, separated by vast voids where matter is sparse. This structure, the cosmic web, emerged naturally from the early universe as gravity amplified tiny fluctuations in matter density left behind by the Big Bang. Over billions of years, denser regions collapsed into galaxies and clusters, while emptier regions expanded and thinned. For a long time, astronomers believed that while this structure existed, it averaged out over sufficiently large distances. No matter where you were, the universe would look statistically similar once you zoomed out far enough. This assumption, called the cosmological principle, is foundational. It underpins how we interpret galaxy surveys, cosmic expansion, and the evolution of large-scale structure. But surveys kept revealing something odd. When astronomers mapped the distribution of galaxies around the Milky Way, they noticed that our local region appeared unusually empty. Galaxy counts were lower than expected. Matter density seemed suppressed. At first, this was dismissed as a local fluctuation, a cosmic coincidence limited to nearby space. But as surveys expanded outward, the underdensity persisted far longer than it should have. The emptiness extended not tens of millions of light-years, but hundreds of millions, then more. Eventually, the data painted an unsettling picture. The Milky Way sits inside a massive, coherent void, roughly 2 billion light-years across. This wasn't a small dip in density. It was a significant departure from the cosmic average, large enough to influence the motion of galaxies, the flow of matter, and the expansion of space itself within the region. Astronomers named it the KBC Void, after the researchers who first characterized its scale and properties. What made this discovery so disturbing was not just the void's size, but its location. We are not near its edge, we are deep inside it, which means nearly everything we measure locally, from galaxy distances to expansion rates, is being observed from within an underdense bubble. And that realization forces a difficult question. How many of our cosmic measurements assume we're in a typical place when we may not be? To understand why the KBC Void matters, we need to understand how gravity and expansion interact. In denser regions of the universe, gravity slows the expansion of space. Matter pulls inward, resisting the outward stretch left over from the Big Bang. In emptier regions, that resistance is weaker. With less matter to slow it down, space expands slightly faster. This means expansion is not perfectly uniform everywhere. If the Milky Way resides inside a vast underdense region, then the local expansion rate we measure, the Hubble constant, will appear higher than the global average. Light from distant galaxies traveling through this emptier region experiences a subtly different expansion history than light traveling through denser cosmic environments. And this is where one of modern cosmology's biggest problems enters the picture. For years, astronomers have been grappling with the Hubble tension, a persistent mismatch between measurements of the universe's expansion rate. Local measurements, based on nearby supernovae and galaxies, consistently yield a higher value. Global measurements, derived from the early universe and the cosmic microwave background, give a lower one. The discrepancy is small in absolute terms, but far too large to ignore. Many explanations have been proposed: exotic dark energy, new particles, modifications to gravity itself, but the KBC Void offers a far more unsettling possibility. Maybe nothing is wrong with the universe. Maybe our location is. If we live inside a massive void, then local measurements are biased by construction. We are measuring expansion from within a region where space expands faster than average. Meanwhile, observations anchored in the early universe reflect the true global expansion rate. Both measurements could be correct, just contextually different. This idea does not eliminate the Hubble tension, it reframes it. The conflict may not be telling us that cosmology is broken, but that our assumption of cosmic typicality is. And if that assumption fails here, it may fail elsewhere too. The James Webb Space Telescope has added new urgency to this picture. Unlike previous observatories, Webb can peer deeper into dusty regions, resolve faint galaxies, and measure structure with unprecedented precision. Its observations are refining our understanding of galaxy distribution, star formation, and black hole growth across cosmic time. And what Webb sees is not always comfortable. In regions expected to be dense, Webb finds fewer galaxies than predicted. In areas thought to host early massive structures, formation appears delayed or altered. When these observations are combined with wide-field galaxy surveys stretching across billions of light-years, the picture becomes clearer. The local universe is not representative of the cosmic whole. The KBC Void is not a theoretical construct. It is etched into galaxy counts, redshift surveys, and the motion of matter itself. Webb's ability to probe deeper and more cleanly strengthens the case that our region of space is genuinely underdense, not merely misunderstood. This has profound consequences. If matter density is lower locally, then galaxy formation proceeds differently. Black holes may grow more slowly. Large-scale gravitational flows behave differently. Even the timing of cosmic events, when stars ignite, when structures collapse, can appear shifted compared to the global average. In other words, our cosmic environment may be subtly misleading us about how the universe works. We may be trying to understand the cosmos using data gathered from a location that is statistically unusual. And once that possibility is taken seriously, it ripples outward into nearly every corner of cosmology, from how we model structure formation to how confidently we can claim to understand the universe's fate. The unsettling implication is this: the universe is not lying to us, but our vantage point might be. Galaxies do not evolve in isolation. Their growth is governed by the environment around them, by how much matter is available to collapse, how often galaxies interact, and how efficiently gravity can funnel gas into stars. In dense regions of the universe, galaxies form quickly, collide often, and grow massive. In emptier regions, everything slows down. Gas accretion is weaker, mergers are rarer, star formation proceeds more cautiously. If the Milky Way sits inside a vast underdense region, then its evolutionary history may be fundamentally different from galaxies living in more typical environments. In a void like the KBC region, matter is spread thin. Dark matter halos are less massive. Gas takes longer to collapse. Galaxies form later and grow more gradually. This can produce populations of galaxies that appear underdeveloped when compared to predictions based on average cosmic conditions. It can also skew statistical surveys, making certain types of galaxies appear rarer or more common than they truly are across the universe as a whole. This environmental bias becomes especially important when astronomers attempt to infer universal laws from local observations. If our region lacks the density needed to trigger frequent mergers, then our models of galaxy growth, calibrated using nearby systems, may systematically underestimate how quickly galaxies evolve elsewhere. What looks like a slow, orderly process locally may be far more violent and efficient in denser regions beyond the void. The KBC Void does not just change how many galaxies we see, it changes the entire narrative of how galaxies live and mature. Supermassive black holes sit at the centers of galaxies, growing by accreting matter and merging with other black holes during galactic collisions. Their growth is tightly coupled to their environment. Dense regions supply abundant fuel. Frequent mergers accelerate growth. Over cosmic time, this leads to the enormous black holes observed in galaxy clusters and massive ellipticals. But in an underdense region, that growth pathway is disrupted. If the Milky Way lies inside a massive void, then the black hole at its center may have grown under unusually starved conditions. Gas inflow would be weaker, major mergers would be rarer, accretion episodes would be less frequent and less intense. This could help explain why some nearby supermassive black holes appear smaller or less active than theoretical models predict. James Webb's observations deepen this tension. Webb has revealed surprisingly massive black holes in the early universe, growing far faster than expected. Meanwhile, local black holes appear comparatively restrained. This contrast makes more sense if early black holes formed in dense regions, while local ones matured inside an underdense cosmic bubble. Once again, our location may be skewing our interpretation of what is normal. The KBC Void does not exist in isolation. It is part of the larger cosmic web, interacting with surrounding filaments and dense regions that border its edges. Matter flows out of voids and into denser structures over time, guided by gravity. This motion creates subtle but measurable effects on galaxy velocities, gravitational lensing, and large-scale flows. From inside a void, these flows appear asymmetric. Galaxies on one side of the void may appear to recede faster than those on the other. Large-scale motions may seem aligned in specific directions. Gravitational influences from surrounding dense regions can produce apparent anisotropies, preferred directions in cosmic motion that challenge the assumption of isotropy. These effects complicate how we interpret galaxy surveys and velocity fields. What appears to be a universal pattern may actually be a local distortion caused by our position within the cosmic web. The KBC Void effectively acts as a lens, not of light, but of perspective, bending how cosmic structure appears from our vantage point. This has implications for everything from dark matter mapping to gravitational flow studies. Measurements that assume uniformity may be subtly biased, not because the universe violates fundamental laws, but because we are sampling it from a region that is fundamentally atypical. The cosmic web is not symmetrical, and from within a vast void it can look profoundly misleading. The disagreement over how fast the universe is expanding has become one of the most persistent problems in modern cosmology. Local measurements of the Hubble constant, based on nearby galaxies and supernovae, consistently produce a higher expansion rate than measurements derived from the early universe, using the cosmic microwave background. This gap has survived years of improved data, refined techniques, and cross-checks. It is not going away. What makes the tension so troubling is that both methods appear internally consistent. The early universe measurements rely on physics that is well understood and extraordinarily precise. The local measurements are based on direct observations of cosmic expansion happening now. If both are correct, then the conflict cannot be blamed on error. It must be rooted in interpretation. The KBC Void offers a strikingly simple explanation. If we live inside a vast underdense region, then space around us expands slightly faster than average. Light from nearby galaxies travels through this emptier environment, accumulating more expansion than it would in a denser region. When we measure distances and velocities locally, the universe appears to be expanding faster than it truly is on global scales. In this view, the Hubble tension is not evidence of new physics but of local bias. We are measuring a regional expansion rate and mistaking it for a universal one. Meanwhile, observations anchored in the early universe reflect the true average expansion of space across all regions, dense and empty alike. This reframing does not trivialize the tension, it deepens it. Because it means that some of our most trusted assumptions may be quietly misleading us. The universe may be behaving exactly as expected, while our position within it distorts what we see. At the heart of this problem lies a deeply ingrained assumption that our location in the universe is not special. The cosmological principle holds that, on large scales, the universe is homogeneous and isotropic, roughly the same everywhere, in every direction. This principle is not just philosophical, it underpins how cosmological models are built and how observations are interpreted. The KBC Void strains this assumption. If we truly reside inside a structure spanning nearly 2 billion light-years, then our environment is not representative of the cosmic average. We are not sampling the universe from a neutral location. We are embedded within a significant deviation from uniformity, one large enough to influence expansion, structure formation, and observed motion. This does not mean the cosmological principle is false. It means it may be more subtle than we assumed. The universe can be homogeneous on the very largest scales while still containing immense regional structures capable of biasing local observations. The question becomes not whether uniformity exists, but how far one must zoom out before it truly applies. From inside the KBC Void, the universe may appear younger, faster, and less evolved than it actually is. Galaxy formation seems slower, black holes appear smaller, expansion looks accelerated. These effects do not require exotic new physics. They emerge naturally from the environment we inhabit. The unsettling implication is that many of our conclusions about cosmic history may be locally conditioned. We may be building global narratives from regional data, unaware that our vantage point is quietly shaping the story. For centuries, astronomy has treated location as irrelevant. Physics was assumed to operate the same everywhere, and observational differences were expected to average out. But the KBC Void suggests that location itself may be a meaningful variable in cosmology, not in terms of laws, but in terms of perception. From within a massive void, the universe looks different. Expansion appears faster, matter appears scarce, structures appear delayed. None of these impressions are illusions, but neither are they universal truths. They are contextual realities shaped by where we are embedded within the cosmic web. This realization forces a shift in perspective. Cosmology may need to account not just for what we observe, but from where we observe it. Models may need to incorporate environmental corrections, ways of translating local measurements into global truths. Without such corrections, we risk misinterpreting the universe's behavior based on a skewed sample. James Webb's discoveries make this urgency impossible to ignore. Webb is revealing galaxies and black holes that defy local expectations, hinting that conditions elsewhere are dramatically different. When these observations are combined with the structure implied by the KBC Void, a coherent picture emerges. The universe is not misbehaving. We are observing it from an unusual place. The idea is both humbling and transformative. It suggests that cosmology's deepest puzzles may not require rewriting the laws of physics. Instead, they may require rewriting our assumptions about cosmic perspective. And if our location can distort measurements this profoundly, then one question looms larger than all the rest. How many other conclusions about the universe are shaped not by what it is, but by where we happen to be? If the Milky Way truly resides inside a vast cosmic void, then some of the universe's most trusted models may need subtle but profound adjustments. Not because the underlying physics is wrong, but because the assumptions used to interpret observations may be incomplete. Cosmological models are built by fitting theory to data, and if the data itself is shaped by an unusual environment, then even the most elegant equations can lead us astray. Standard models of cosmic structure formation assume that large regions of the universe behave statistically the same. Galaxy formation rates, merger histories, black hole growth, and expansion measurements are all calibrated using observations from our cosmic neighborhood. But if that neighborhood is underdense, then those calibrations inherit a bias. They reflect a universe with less matter, weaker gravity, and slower structural evolution than the cosmic average. This realization forces a careful re-examination of long-standing discrepancies, the apparent mismatch between early and late galaxy growth, the surprisingly rapid emergence of massive black holes in the early universe, the difficulty in reconciling local measurements of expansion with global ones. Each of these tensions may be influenced, at least in part, by the environment from which we observe them. In this context, the KBC Void does not undermine cosmology. It refines it. It suggests that models must explicitly account for environmental variation, rather than assuming it averages out automatically. Once that adjustment is made, some of the universe's most stubborn puzzles begin to look less like contradictions and more like perspective effects. Cosmology may not need new laws. It may need a better map of where we are standing. The implications of the KBC Void extend far beyond explaining existing tensions. They point toward a future in which cosmology becomes increasingly location-aware. Upcoming surveys and observatories are already pushing in this direction, mapping galaxy distributions and matter density across unprecedented volumes of space. By extending observations far beyond the boundaries of the void, astronomers can directly compare underdense and overdense regions, measuring how expansion, structure formation, and galaxy evolution differ across environments. These comparisons will allow scientists to separate truly universal behavior from locally conditioned effects. In doing so, they will transform how cosmic measurements are interpreted. James Webb plays a critical role in this effort. By observing distant galaxies formed in regions far removed from our own, Webb provides a glimpse of how the universe behaves under different conditions. These observations serve as a counterbalance to local surveys, anchoring cosmological models in a broader, more representative sample of cosmic environments. As data accumulates, the KBC Void will no longer be an anomaly inferred indirectly. Its boundaries, density profile, and influence will be mapped in detail. And once that happens, cosmologists will be able to correct for its effects with increasing precision, refining measurements of expansion, matter distribution, and cosmic history. In this way, the void becomes not an obstacle, but a tool, a natural laboratory for understanding how environment shapes the universe. The most profound lesson of the KBC Void is not technical, it is philosophical. For centuries, science has progressed by removing the observer from the equation. The laws of nature were assumed to operate independently of where we stood, and in a fundamental sense, that remains true. Gravity works the same everywhere. Physics does not change from place to place, but observation does, perspective does, context matters. The KBC Void reminds us that the universe is not obligated to make our measurements convenient. It does not guarantee that our location is typical, fair, or representative. We are not placed at the center, nor at an average point. We are embedded within a vast structure shaped by chance and cosmic history, and that structure quietly influences everything we see. This does not diminish our understanding of the universe, it deepens it. It tells us that reality is richer, more textured, and more complex than simplified assumptions allow. It tells us that even on the largest scales, context matters, that where you observe the universe from can shape what you believe the universe to be. If we are willing to embrace that humility, then the KBC Void becomes something remarkable. Not a flaw in cosmology, but a revelation. A reminder that understanding the universe requires not just better instruments, but better perspective. The universe has not been hiding the truth from us. It has been showing it to us all along, through the subtle ways matter clusters, space expands, and galaxies move. We are only now learning how to read those signs without mistaking our own vantage point for the whole of reality. And in doing so, we take one more step towards seeing the universe not as it appears from here, but as it truly is.